Welcome back to Cartoon Physics. In this video, we'll be taking a final look at what would happen to Ant-Man if his mass remained constant when he changed into Giant Man. In the previous videos, we calculated his initial acceleration and his terminal velocity. This time, we'll calculate his maximum height that he'd reach as he floats upwards. The buoyant force is a function of the density of the fluid that's being displaced. Once Ant-Man reaches a height where his density is the same as the surrounding air, the net force will be zero. When Ant-Man's mass equals the mass of the displaced air, he'll float in equilibrium. We'll use this equation for estimating air density, published by the University of Hawaii. Along with estimating air density, we'll look at some properties of logarithms and exponents. Let's get started. Remember that his upward motion is caused by the buoyant force. If Ant-Man's density were the same as that of the air around him, and he'd float in equilibrium. In our equation, rho naught is the density of air at sea level, z is the height that we want to solve for, and h is a scaling factor. When we plug in our scaling factor for the height we want to solve for, something interesting happens. The exponent becomes -1, and our equation simplifies to rho naught over e. This means that when we've reached a height of 8,000 meters, our air density has been reduced by a factor of 1 over e. Interestingly, this is the death zone of Mount Everest. This is where there's not enough oxygen to survive, and air density in the death zone is about 1/3 of that at sea level. We'll rewrite our equation, and we'll have a symbolic term for Ant-Man's density. Again, this is his mass over his giant volume. And we want this to be equal to our equation for air density. This is the density of air at sea level and Ant-Man's giant volume that we solved for in the previous problems. And we'll write down a few digits of E. Along with our algebraic manipulation, we have the first property of logarithms, which is the natural log is the inverse function of the exponential function. So the natural log of e to the n equals n. The second property of logarithms is that the negative of the log of a over b equals the log of b over a. We'll use the first property of logarithms to remove the exponential function from the right-hand side and add a natural log to the left-hand side. Note the negative sign. We're going to use the second property of logarithms to remove this negative sign and flip the numerator and denominator. Now we have a symbolic expression for z, and we can plug in our values. One last property of logarithms is that the argument should always be unitless. This checks out because we have kilograms over kilograms and meters cubed over meters cubed. And it looks like Ant-Man's final height is in the upper stratosphere. Ant-Man's final resting height is above 32 kilometers. This is about 11.5% higher than what I found with a more sophisticated atmospheric calculator. So you can't use it for NASA, but it's close enough for cartoon physics. And on that note, thanks for watching, and we'll see you next time.